Today I'm going to talk about applications of PyTorch Autograd in physical simulations. Next slide, please. And my talk would be divided in such topics. First, I'll talk briefly about motivation, then I'll talk about where Autograd being used, then I'll talk about algorithmic problems, and about my paper where we use PyTorch Autograd much more efficiently to make everything scale better on practice. Next slide, please. So why we need to simulate physics, and especially quantum physics? And it had many practical applications where it is actually crucial. We need to do it for drug discovery. We need to do it for simulating quantum computers on classical computers. We need to do condensed matter physics simulations because, well, we want to predict how actual real-world systems that obey quantum laws, how they behave, so that we don't need to actually build some experiments and we can just run them on the computer. But there are major problems that exist with the existing canonical classical methods. They're not scalable to quantum physics. Because when you try to solve equations of quantum physics on a classical computer, you get that you cannot basically do even two-dimensional simulations because they just don't scale well with the number of particles that you want to consider. And for chemistry, for example, we need to simulate many particles. We need to consider systems with hundreds of electrons. And that's just not feasible to do with the classical methods that exist. And here's where deep learning comes into play. It is scalable, and actually deep learning basically free of these curves of dimensionality that arises in classical methods, because it actually can scale just linearly. You have thousands of electrons. Well, you just need 1,000 more compute than you needed for one electron. Unlike classical methods that basically there is no computer that can be used to simulate it. And that's where Autograd arises, because it's being used to evaluate those equations with neural networks. Next slide, please. And so here's on the slide, you can see some equation, and that doesn't actually matter what that equation is about. It just exists, and that's what physicists use to describe quantum physics. And how deep learning arises there and it's being used. So we just say that that function that arises in Schrödinger equation, it's now a neural network. And we want to basically just minimize error of this equation on some grid of points, of cloud of points. And that's it. That's basically where Autograd being used and how neural networks being used for simulating physics. And Autograd being in particular used just to estimate those delta-looking operator is called Laplacian. And it's used to estimate a derivative with respect to time. And that's it. We just minimize such quadratic error. But there are some other issues. In particular, this Laplacian is actually not very scalable with the Autograd. And I'll talk about it. And first, I'll talk about Autograd, what it does. Next slide, please. So the basic function that exists in PyTorch Autograd, it is just function grad, how not surprising. And what it does, it computes Jacobian vector product. And that's like one of the main concepts that are implemented in PyTorch. And we just pass three major inputs, like our function that we want to compute. In our case, it is just neural network evaluated on some point And we pass with respect to what we want to differentiate, whether it is coordinates or time. And we pass our direction with respect to which we want to differentiate. And that's basically it. And maybe to clarify a bit, the same thing happens when we do backpropagation in deep learning. It computes also gradient, and then it backpropagates, and that's how weights are being learned. The major difference is that instead of differentiating weights, we want to differentiate actually input features of that neural network. Next slide, please. And so what is the Jacobian that Autograd calculates? It is just a matrix of all partial derivatives of our neural network. And Jacobian vector product is just when we multiply this matrix by this vector. And interesting thing about it, why it's so important and why PyTorch built their Autograd library around Jacobian vector product is that it has the same algorithmic complexity as just forward pass of the neural network. So if you can compute a forward pass in a linear time with respect to number of your particles, then you can compute Jacobian vector product in the same time. Well, it would be a bit slower, but that doesn't matter. At least it scales asymptotically the same. And that's very important for this talk I am giving. Next slide, please. So, as I mentioned previously in the Schrödinger equation, and like in any other equation that appears in physics, like heat equation, or any equation that appears actually in finance, like Black-Scholes, there is a term that is a Laplacian of our neural network in this case. And it poses a major problem. It doesn't scale so well as Jacobian vector products. And the reason is, to compute Laplacian, you need do Jacobian vector product n times, and that makes it scale like a quadratic function. And that's problematic. That's kind of better than classic numerical solvers that scale exponentially. But it's still quite bad, because maybe you can simulate 10 electrons, 100, but 1,000 is no longer feasible, because quadratic function grows quite fast. But you can use some tricks. Like one of the popular tricks is to use Hutchison estimator that allows to estimate a Laplacian using stochastic estimate, using Jacobian vector products. And that scales linearly, but you need larger batch sizes. And essentially, it doesn't scale linearly still, because your batch size should grow actually faster than constant. So that's a problem that exists with the quantum physics simulations. Even if we do neural networks, it doesn't scale well. So next slide. Next. Oh, okay. So I'll talk just briefly about a paper that I wrote with my co-authors. That paper had a fancy name, Deep Stochastic Mechanics. And that's a nice picture of what we do in the paper. And essentially, we, instead of trying to learn neural network, we instead trying to learn a diffusion model that samples from a wave function. And apparently, it's much easier problem to do than to learn the wave function. And it can be proven theoretically that it's actually equivalent to learning wave function, but you don't need to learn wave function. You can actually learn sampler from it using a diffusion model. And interesting thing about it is that equations that appear there, they actually can be optimized with Jacobian vector products and scale much better than original Schrödinger equation. And that's like one of the major contributions, that we can solve a bit different problem that is equivalent to original quantum mechanical simulations, but we can use Autograd much more efficiently and scale linearly with the dimension. Next slide. So here's some other equations that we use, and that doesn't actually matter what those equations mean. Important thing is that there is no Laplacian anywhere. It purely relies on Jacobian vector products. And this operator on the right side, it is the same as just Jacobian vector product applied to Jacobian vector product. And it works fast. And important thing that, as I said previously, it is equivalent to the Schrödinger equations, but doesn't have Laplacian anywhere. Next. One back. Previous slide. Yeah. So that's some code snippet just to show how easy to evaluate this composition of Jacobian vector products that appear in our equations. And as I said, PyTorch implementation of Jacobian vector product scales well in the same time as you do forward pass of your neural net. And compared to Hutchinson estimator, it has no variance whatsoever. So we can use small batch sizes and still get convergence. And that's like quite interesting thing for me. But here's a caveat. Generally, we cannot just replace a Laplacian with this weird operator. And we just got lucky in this work that apparently just for equations that you saw on previous slide, we can do this, but generally we cannot. But there are some conditions theoretical when we can do, and they sound like that solutions to the equations have full gradients. If they are full gradients, you can throw away Laplacian and use this operator. So next slide. And we actually did numerical simulations of how well it scales. So here's on a plot, blue line shows when we use a Laplacian in equations with Autograd. And it is, as expected, scales quadratically. And on axis X, we have essentially a number of particles that we consider. And our version that relies just on a Jacobian vector products, it scales linearly as we expected theoretically. And we also compared not just how one epoch scales, but that we can get our loss to the level below some epsilon value, and it also scales linearly. So this is quite huge for simulating quantum physics because it allows to scale it to thousands of electrons potentially without being cursed with dimension-related problems that appear in classical solvers or in physics-informed neural networks that use a Laplacian. Okay, next slide. And this is last slide with some pictures of how well it works. So I'll be happy to answer any questions.